Okay, in the last class we have seen okay. Okay, this is the lecture number 8. Okay, and one more thing, it's a continuation to the last class, MOSFET behavior. Okay, what is the recap? What is we have learned in the last class? So that means we have compared the gate potential with the source potential. Okay, and based on that one, that the difference is compared with the threshold voltage. Okay, whether it is greater than threshold voltage, and MOS transistor is on. If the difference is less than the threshold voltage, the PMOS is on. Okay. Therefore, let me consider here. Let me conclude. So, for an NMOS, okay, for an NMOS transistor, what is the condition? VG, yes, should be positive, right? Should be positive. And this is possible by, it is possible by making VG is more positive than VS. Okay. Increase the VC in the positive direction, decrease the VS in the negative direction, then definitely you will find the transistor becomes on. Okay. Okay, it is for the on, okay, for the purpose of on. For PMOS is set to be on. Okay, for PMOS set to be on, what we have to do? VCS should be negative. It is possible by making VC is more negative than VS. It should be more negative. Okay, let me write the word more negative. Here also more positive. More positive than. I've given the explanation, clear explanation on that why it is so with the help of different combinations, I'm sure, right? Now, so far we have seen that the MOSFET is compared based on whether the condition is on or off. Okay, if you meet this condition, the MOSFET is on. Otherwise, MOSFET is off. Once the MOSFET is on, then we should say the current will flow, but the current is not uniform because certain voltages of the drain potential, certain values of the VDS, it is a linear relationship, and certain values of the VDS, this will be constant. Therefore, we have to think about it. Okay. Again, I'm going to take this exercise. Okay. Let us consider. Okay. Let me take this is the gate oxide. On top of it, we have a. Okay, now we okay, better I have to take the little bit bigger one because intentionally I want to make it bigger. We'll take this the one, and on top of it we have a gate potential. Okay. So this is a M plus This is also n plus. Okay, so we have to apply positive here and negative on the back. We connect here positive and connect the negative here. Okay. And now the question comes here is, okay, this point we have already discussed about this one. Okay, but I'll take another color. Okay, so therefore this is a negative. Okay. Now here we take that this is the positive, potential, and this is a negative potential. We have to apply here and here. Okay. We take the same copy and understand about the PMOS as well. What we can understand here, what we need to remove, instead of n plus, we have to use p plus. Okay. Now, what is this is called? This is VC. This is called VD. This is called VD. This is called VZ. Okay. So now this is called VD. Yes. Am I right? Drain to source. I'm writing this one. What about this one? VD. Yes. Okay. Now we want to compare the difference between these two. Okay. If we take this is the NMOS transistor. Okay. This is the drain potential. This is the gate potential. Okay. I want to compare these two things actually now. Okay, this one to this terminal voltage I want to consider. Similarly for the PMOS as well. This is the drain potential and the gate potential. Okay, let me call this is a VD and this is called VC. This is VD, VC. Okay, keeping sources aside now. Okay, right. So what happened if the drain potential is more than that of the gate potential? See, both are positive potential, as you can see here. This is also positive. This is also positive, right? If the gate potential is more than that of the drain potential, the question is, if the VZ value is greater than that of drain potential. What do we observe? That means that if the gate potential is more, means that we are applying the more positive. And is that true? So this is initially, but now we are increasing more and more. Am I right? What will happen to this one? Definitely channel will be formed without have any problem, right? Therefore, under this condition, okay. But the question is that how much bigger than this one? How much more positive of the VC compared to the VD? That's the question. Okay. If this value is at least, if the gate potential is at least more than that of the threshold voltage, okay, that means whatever the drain potential is there, just add threshold voltage to it, and that result, the value of this one is the VC value, then definitely the MOSFET is the channel will be formed from source to drain without have any problem. Okay. Under this condition, the MOSFET, the current equation for this one is it follows the IDS in the linear fashion. That means the drain potential plus threshold voltage value, okay, which is less than that of the gate potential, or the gate potential is more than that of drain potential plus threshold voltage, then the channel will be formed without having any problem. Okay, therefore the current will flow in the linear relationship. The current will flow linear relationship. Therefore, here in this case, this is actually the more positive. This is a more positive than this one. Okay, for example, this is more positive. And the three arrows represents the more positive than the VDS. Just one threshold is above the drain potential makes the transistor enter into linear threshold. Okay, now look at this condition here for the PMOS. Oh, I'm so sorry. The PMOS, I need to change this one, right? It's not this one. What is this? It is positive. It is negative. Positive and negative. Okay. If the VC value is more negative, VC value is more negative than VDS. What I'm going to write? Look at this one. The VC of this one is VC of the PMOS transistor is more negative than the drain potential plus threshold voltage. Okay, that means what is this value of this one now? The drain potential is actually more negative. That means it's in the lower part of the more negative side. Okay, so than that of the drain potential. Okay, then MOSFET is said to be in linear, right? IDS is said to be in linear. Did you catch this point? Did you catch this point? If it is more positive and negative that you have to apply here, okay, the holes will be developed here. If you apply more and more negative, then definitely, effectively, the channel will be crossed all over the silicon dioxide area. Okay. So this is also said. This is also something else we can write. Therefore, the drain to source potential is less than gate to source potential minus of threshold voltage. This is another way of looking at the equation. Okay, but inherently that is what the meaning of it. Okay. Similarly, here also, what is the VDS? Can somebody help me? VDS value is greater than VGS minus of VTH. Did you catch this point? So therefore, the channel is effectively formed from this portion to this portion. The channel is available from this one to this one. Okay. The second option, if the VC value is less positive than that of the drain potential. What is the next possibility? When the gate potential is what I can write here? Less positive than this one. Okay, now the drain potential is more and the gate potential is less. How much less this is? At least one threshold less of the gate. At least one threshold less of the gate potential. Okay, under this condition, what will happen? Under this condition, what will happen? If the drain potential is more, means what? As we have seen in the previous class, the depletion region will become increases, right? Sometimes this one. If you increase more VD, then some more region will be increased. If you increase more, then what will happen? Increase. Okay. Therefore, as you can see here, this portion is actually free of carriers, right? You can see. As you can see, these are all free of carriers. That means this side is increases more, electrons are increases more and more, and this side something like this is going on there. this in this way. Are you getting the point? The channel is not uniform. Here you can see, observe this one. Channel is not uniform. It's just like, the structure. That means this particular portion does not have any free carriers, right? Okay, that means under this, near the drain, you can see there is no inversion channel. Under the drain, you can see there is no inversion channel. Okay, but it is since the MOSFET is actually VGS is greater than threshold voltage, definitely the carriers can move from source to drain. Okay, because of the drift velocity, the carriers can move. Because of the drift velocity, carriers can move from this one to this one. The carriers can move, but this value is a constant. Okay, so therefore, what I can say here now, if the gate potential, sorry, if the drain potential is okay more than that of gate potential, at least less than that of this one. So the gate potential should be, the drain potential should be one threshold less than that of the gate. At least if we maintain, then definitely near the drain, more depletion is possible. Then no inversion is not available. Then definitely the constant current will flow. Okay. So therefore, under this condition, the MOSFET is actually said to be in linear. Sorry, saturation. Saturation. MOSFET is said to be in saturation. So now, this is also possible to say that people will call VDS value is greater than VGS minus of VTH. This is also possible to say. Okay, the drain potential is more than that of the gate potential. But shall we apply the same thing here in the PMOS? Now you tell me what way that I can write. Can anyone? What should be the drain potential now? The drain potential is more negative or less negative? Look at this board. Okay. So in the previously we have seen that VG is more negative than the drain. Now, if the VD is actually, we want to make it more negative than the gate. Okay, then what will happen? If the VD is more negative, what will happen? It is a reverse bias, right? P and reverse bias, right? Here actually, it forms a reverse bias junction, right? So what is the reverse bias junction here? Actually, it forms a depletion region. Towards the channel side, more depletion region is existed. And this is what the width of the depletion region towards this. Therefore, near the drain, you see no inversion. And near the drain, you can see no inversion. If there is no inversion, when this no inversion is happening, as we can see that VD is actually more negative. VD must be more negative. More negative means what we can write it less than or greater than. I have to write VD. VD is less than VG minus of VTH. At least the show voltage must be less, right? Okay. Now, this is also so now in this condition, the MOSFET is said to be, IDS is actually follows the saturation current equation. Now, what about the VDS? This also say that VDS value is less than VGS minus of VTH. That means VDS value is more negative than that of the. Did you catch this point? The negative values, I'm talking about the negative values as well as the positive values, the simultaneously. Please remember this way. Okay. Okay, right? Okay. So therefore, now if I give you a MOSFET actually, okay, if I say that, for example, NMOS transistor, if I give you NMOS transistor, now if I ask you to operate this particular NMOS transistor in saturation region, then what potential that you apply at the gate and what potential that you apply at the drain? Saturation. More positive where we need to apply? Drain, right? Drain should be more positive than that of the gate. What is the minimum condition? If I say the minimum, at least minimum, this much should be maintained. At least threshold. Okay? At least we have to maintain the difference between these two must be threshold voltage. Otherwise, it won't happen. Huh? Right. So, for example, if I give the PMOS transistor, I ask you to keep the MOSFET in the linear region. Then what potential you apply at the gate, what potential that you apply at the drain? Linear region. Gate should be more negative than that of the drain potential. Drain, what is the drain gate potential? Linear or not? Linear means that the gate is always more negative. In the negative direction I'm talking about. And drain should be at the more positive direction. Okay, that's what we have to. Okay, so let me conclude this point also. Okay, what is the conclusion that we can do? We can draw here. For NMOS said to be linear. Okay, the drain potential, the gate potential should be more positive than drain potential. Okay, what is the minimum condition? At least the gate potential should be one threshold above the drain potential. Okay, what I can write? At least gate potential should be one threshold more than drain. Okay, whatever the drain potential is there, just one threshold if you add it, and that much value that if you apply at the gate, then it should be in linear region. Okay. Similarly, what equation, what statement that I can write here again? That the MOSFET is said to be in okay, what we can write it here? It should be okay. Let me consider this is a saturation. The gate potential. Now, instead of the gate potential, we can call it as the drain potential. Okay. In the linear point of view, we call it as a drain. We use the drain is a terminal more importantly than the gate. Sorry, the gate than that of the drain. For saturation point of view, drain potential we talk more than that of the gate potential. Okay, so we'll go and write the drain potential should be more positive than the gate potential. But the minimum requirement at least, what is the minimum requirement? At least drain potential should be one threshold less than one threshold less than gate potential. Okay. Whatever the drain potential that you want to apply, okay, that should be greater than that of the gate potential minus threshold. Whatever the gate potential is there, gate potential, you reduce one threshold, and that value we have to, more than that value you have to apply. Okay. So sorry, more than, I think it's more than the difference between the gate and the one, right? Yeah. Okay. Drain potential should be more than. Okay. Therefore, we'll go and write the same equations for the NMOS as well, PMOS as well. Okay. It is okay. I think explain it. It is a. Can you invert this particular one for the PMOS? Okay, I'm unable to write that one. Okay. Okay, let me for the PMOS. For PMOS. Linear. For PMOS to be linear, what is the condition? The gate potential should be more negative than drain. Okay. For the saturation, for PMOS to be in the saturation, the drain potential would be more negative than drain. Sorry, gate. Okay. Of course, at least threshold voltage we have to maintain in the case of this thing. Okay. Now, therefore, finally, for example, if you take this is an NMOS transistor, this is a PMOS transistor, for example. Okay. Therefore, VB, VS, VG, VG, VS, and VB. For example, something like this. Okay. Okay. So if you want to make this transistor is a linear region or saturation region, what we have to apply. So if you compare this drain potential and gate potential, for example. Okay, if you want to make the NMOS is wants to operate in linear region, NMOS is want to operate in linear region, what we have to do? This must be more potential that we have to apply than this one, right? Okay, this is a less, because both are positive direction. Okay, what about here? Linear region. If it is more negative that we have to apply than this one. Okay, that means if the gate side is actually the NMOS case, gate side must be more and more that we have to apply. Positive potential we have to apply than the drain potential. Whereas a PMOS transistor, we have to apply more and more negative potential we have to apply than that of drain potential. Okay, if suppose the drain is decreasing more and more for a NMOS transistor, what does it mean? If the drain potential of the NMOS transistor is decreasing more and more, then what does it mean? It will be enter into the linear region. If the drain potential is decreasing and decreasing, that means that what? It will enter into the linear region. If the drain potential increases more and more than that of the gate potential, saturation region. But whereas in the PMOS, if the drain potential is, okay, this is the down, right? Yeah. If the drain potential is decreasing more and more compared to the gate potential, it will be in, if the drain potential is decreasing more negative than that of the gate, if the drain potential is decreases more and more than this one, it is in the saturation region. Okay, so therefore please remember that it is drain is actually decreasing more and more, means that it will enter the saturation. If it increases, drain potential increases more and more, means that it enter into the linear region. Okay, please remember that. So actually, we want to operate the MOSFET in the analog circuit design or analog IC design. We want to use the MOSFET must be operated in saturation region. Must be operated in saturation. In analog application. Analog applications. Please remember this one. The MOSFET is said to be operated in saturation region under analog circuit design. Okay, so please remember that one. We have to always MOSFET should be in saturation region. If you want to make the MOSFET set to be in saturation region, what is the condition for the NMOS transistor on the drain? Drain should be more positive than that of the gate. Okay. Similarly, what is the condition for the PMOS transistor to be set to be saturation? Drain potential is more negative than that of this one. Okay. So that means the NMOS case, we have to increase the drain more and more. In the PMOS case, we have to decrease the drain more and more in order to make both are in saturation. Get the point? In the drain point of view, I told you. For example, if the gate point of view, if I talked about this one, what you can say? Gate potential should be far less than that of drain potential. Whereas in case of PMOS, it should be more positive than that of the drain. Okay. So therefore, anyone is if anyone whatever it is you would like to remember, you can remember. But if the gate is drain is more, people will talk about the more on the drain. Okay. If the drain potential is more and more, okay, but the NMOS will be in saturation. The drain is more and more negative. Okay, the PMOS is saturation. If the drain is more and more positive for the NMOS, sorry, PMOS. It should be linear. Whereas in the NMOS, the more and more negative of the drain of the NMOS are more and less negative, less positive, then what will happen? Linear region. Okay.
So that's what you have to remember that whenever I change something, then you have to remember that phrase. Okay. So therefore, the bottom line is one bottom line I will talk about. We can complete this course. Okay. So the bottom line is, what is the first bottom line?
For the PMOS, drain should be more in order to make that in saturation. For NMOS, so I'm so sorry. For NMOS, drain should be more. For the PMOS, drain should be less. Compared to gate, you should say like that. Compared to gate. Okay. That's what we compared to gate and the threshold voltage. Altogether, we have to say like that. But by looking at directly, then we can say that if the drain potential is more, then definitely blindly we can say. But definitely we have to take care about the threshold also, and accordingly we have to take that. Okay. So this is how we have to talk about the MOSFET behavior. Okay, by changing the gate source voltage, by changing the drain to source voltage, both for the NMOS as well as the PMOS. Very, very important one. Okay, we will see some more basics on this MOSFET tomorrow in the next class, and we will see some tutorial problems also. Okay, we stop here today.